let's look a little more at the periodic table. So Dmitri Mendeleev is often given credit as developing the periodic table. So this happened back in 1869. He noticed that certain groups of elements had similar properties. And so he was, at that point we had not found all the elements yet, but there were a bunch of them and it was kind of a mess. I mean, how do you organize all this information? So he's, playing around and trying to figure out what are the patterns in here. And so he found that if you put the elements in order of increasing mass, the smallest one first up to the heaviest one, that those similar properties recurred in a periodic pattern, kind of like keys on the piano keyboard, right? There's the note C in the middle, and you go up an octave and there's another C and another C and another C, and there's a pattern there of this repeating property. Periodic is a term meaning exhibiting a repeating pattern. It's every so often, right? It's a periodic pattern. So here are the first 20 elements listed in order, and a little bit like a piano keyboard where this might be C and C and C. We see these repeating patterns. The orange ones have the same pattern, some similar properties, and the green ones have similar properties, etc., blue and purple. There's patterns. And so he summarized his observations in what's known as the periodic law. When elements are arranged in order of increasing mass, certain sets of properties recur periodically. No explanation of why this is, but he said, hey, I noticed this. This is true. So he took that and, it's just sort of awkward to have this long, long list of elements. So he put them in a table such that elements with the similar properties ended up in columns on top of each other. And so this is just the first 20 elements arranged like that. Hydrogen is kind of an exception to everything, so he's sort of sitting here by himself. Helium is over here on top of these guys. And then we've got lithium, sodium, and potassium. Those have similar properties. Beryllium, magnesium, calcium. They have similar properties. So on our periodic table, elements that are in the same vertical column have some similar properties. We call them families, element families. And as we know from looking at people, the children from the same family often have some things in common. If you look at my children, you're like, wow, somebody made them with a cookie cutter. They're just like, it's just so obvious that they are a Kawagoe. Other people in other families, the children may look quite different, but there's still something that is similar about them, okay? And so we see in these families of elements that some of them are very similar to each other, and some of them only have certain things in common, but there's a similarity, and so elements have families. The table that Mendeleev made had some gaps in it, because he's putting them in order of with the properties lining up, and sometimes he had to leave a gap. And so he predicted that we would find an element later that would fit in that gap, and he even predicted the properties of those elements, and he was actually really close with his predictions. One of the ones he predicted was one that he called ecosilicon. Eka is just a prefix that means below. So this is the element that was supposed to be below silicon. It hadn't been discovered yet. 1886, Clemens Winkler discovered it, and he named it germanium because he was German, so he named it after his country. This is just kind of interesting. A color-coded periodic table showing when these things were discovered, when the different elements were discovered. So silicon here was discovered before Mendeleev was working on the periodic table, and this was germanium was discovered afterwards. And these guys down here have all been quite recent. Many of those are man-made. Any questions? And this is how, in 1869, Dmitri Mendeleev completed his first periodic table. Chemistry Tetris. In our modern periodic table, the elements are not listed in order of increasing mass, but in order of increasing atomic number of protons. Most of the time, increasing mass and increasing atomic number go together, but there are a couple of exceptions. Let's see if I can find them. 52 and 53, tellurium and iodine. So tellurium has 52 protons, it has a mass of 127.6. Iodine has 53 protons, but a mass of 126.9. So iodine atoms on average weigh less than tellurium, and yet they're above in the periodic table because the true ordering principle is atomic number. And when Mendeleev made his periodic table, he did put them in the correct columns. He's like, well, this one's less massive, but it really belongs over here. And that's part of what led to, well, maybe it's not specifically the mass that is the ordering principle. And of course, our modern periodic table has more elements than Mendeleev's did because we've discovered new ones and made new ones. There are some major sections, divisions in the periodic table. One thing I hope that you'll come away from this class with is an appreciation for the periodic table and the vast amount of information that is hiding in it. Okay, I'm going to try to reveal some of that to you. So there's this stair-step line, and that divides the nonmetals from the metals. Okay, along the stair-step line, these lavender-colored elements are what we call semi-metals or metalloids. They're between metals and nonmetals. They're kind of neither and both at the same time, right? So they're in between. And we notice that hydrogen's hanging out over here. Hydrogen gas is obviously a non-metal, and yet he hangs out over here. And we're going to find that hydrogen is like the baby brother of the element world, and he just violates all kinds of rules. He's got to be the exception to everything. We all know one of those people, right? Everybody's doing this, but no, this person has to do it different. That's hydrogen. These pictures here are just kind of for your information, interest, some pictures of some of the elements. We also have some numbers here, 1, 2, 3, 4, 5, 6, 7. Some periodic tables actually list those numbers, others do not. The periodic table on the wall does. Those are the periods, the rows of the periodic table. And then we have numbers at the top of each of these columns. There are two sets of numbers. The periodic table on the wall has both of them. This one also has both of them. So there's one way is just to number them 1 through 18. That's the International Union of Pure and Applied Chemistry's preferred method. The other method with the A's, on this periodic table, there are Roman numerals with A's and B's. 1A, 2A, all of these guys are B something, 3A through 8A. That's the current US usage. Since we're currently in the US, that's what we're going to use. I think it's a lot more descriptive. It helps us get more information. There are some similarities. If you notice here, what IUPAC calls column 13 is column 3A. If you just knock the first digit off, the numbers are the same. Okay. Then there's these guys down here. What's up with them? Well, here we've got lanthanum's 57, and it jumps to 72 for hafnium. What's up with that? Well, the periodic table that we have on the wall is actually how the periodic table should be. We cut it and made it that way because it fits in the space above the chalkboard. But that's really how it should be. And so over here, we see that the numbers go continuously. Here we've got barium, lanthanum, cerium, 56, 57, 58, and it continues and comes over here 71, 72. So these guys get pulled out of most periodic tables. This first row here is called the lanthanides because they come after lanthanum. And this, there's that issue again. The actinides are called actinides because they come after the element actinium. So the full, very wide periodic table works in our classroom. Doesn't work real well on screens and pieces of paper. These guys at the bottom are pretty rare. We don't use them very much, and so we cut them out and we stuck them at the bottom. Okay. So any questions? You need to know the metals, nonmetals, and semimetals. In terms of recognizing which is a semi-metal, personally, I don't care about polonium. It's an odd one, and we don't come up on it much. So the way I remember this is everything that's touching the line on a side is a semi-metal except aluminum. So we have experience with aluminum. Aluminum pans, aluminum structures, right? Aluminum is a metal. So everything that's touching the line, call it a semi-metal, except for aluminum. There's polonium too, but it's not going to come up, so don't worry about him. So we classify the elements into these different groups: metals, nonmetals, semi-metals. And they have some common characteristics. Metals are good conductors of electricity and heat. They're malleable. If you bang them with a hammer, they dent and smash, and you can hammer them flat. They're ductile. You can draw them into wires. They're often shiny. Most importantly for chemistry, they tend to lose electrons when they undergo chemical changes. So metals tend to lose electrons. The nonmetals, their physical characteristics are not as uniform as the metals. They tend to be poor conductors of heat and electricity. They're not malleable, not ductile, and they gain electrons. So they're kind of opposites, right? We have the metals, and then we have the non-metals, and they're just basically opposite. Then the metalloids or semi-metals are in between. They have very mixed properties. Several of them are considered semiconductors. And these are really important in technology. Semiconductors are an essential part of all computers. Okay? They're very useful because they have intermediate electrical conductivity, and we can alter their conductivity by things that we do to them. They're also very temperature dependent in that conductivity. So you should be familiar with these broad characteristics. Here's another periodic table. So here are the periods and the group numbers. Talked about those. And another way to divide things up is by main group elements and transition elements. So this part of the periodic table is lower. That's the transition elements. This is like, actually it kind of looks like water, right? So there's the blue water, and here's one cliff, and there's another cliff. This is the transition from this one side to the other. These are the main group elements, the mainland, and the water is in between. Main group and transition metals. Transition elements, technically. Some of the groups have names. The noble gases are group A, 8A. They are very unreactive. The alkali metals are group 1A. Those are very reactive metals. The alkaline earth metals next to them in group 2A are fairly reactive, but not as much so as group 1A. And then we have the halogens in group 7A. And those are very reactive nonmetals. No, I thought I had a periodic table again. So the noble gases over here in group 8A, these are the halogens. In group 7A, they're nonmetals, and they're also reactive. The noble gases are not. These are the alkali metals. Hydrogen is, hanging out over there. Is he a metal? No, but he's hanging out there. So these guys are the alkali metals, very reactive, and the alkaline earth metals, not quite as reactive. The other groups don't have names that we're going to care about. So I told you earlier that metals tend to lose electrons. Metals that are in the main group, those sections that stick up, lose electrons, and they're going to form a cation that has the same number of electrons as the nearest noble gas. And the main group nonmetals tend to gain electrons, and they'll form an anion, a negatively charged ion, with the same number of electrons as the nearest noble gas. We'll find out why later the noble gases are so special. I have a periodic table coming up. Okay, it'll get there. Sorry if I'm making you dizzy. So the alkali metals, group 1, 1A, have a tendency to lose one electron, form 1+ ions. When we talk about the charge on an ion, we put the charge symbol after the number. So group 1 makes a +1 ion, or a 1+ ion. Group 2 makes a +2 ion, and they do that by losing 2 electrons. So that's not a coincidence. This is group 1, and it makes a 1+. Group 2 makes a 2+. Over here, the halogens over in group 7A, the nearest noble gas is one column to the right. If it gains 1 electron, it'll have the same number of electrons. And so they form 1- ions. And then the oxygen family doesn't really have a name, but that group 6A, tends to gain 2 electrons, making a 2- ion. So one way we can remember this is that main group elements that form cations with a predictable charge, group 1A and group 2A, actually, and group 3A, the charge is equal to the group number. So a metal in group 2A forms a 2+ ion. A metal in group 1A forms a 1+ ion. For the main group elements that form anions, the nonmetals, the charge is equal to the group number -8, or I'll show you another way as well. So the main group elements tend to have predictable charges. The transition elements are just all over the place. Okay, so here we have the noble gases. They are not listed here because they do not form any ions. They just don't react. They're just like full of themselves. They're like, we are so cool, we don't need anybody else. I think of them as being that in-group in high school that everybody's trying to be like. And electrons are like your clothing, right? So these other elements that are not part of the noble gas group are trying to look like the noble gases by changing what they're wearing, by changing their numbers of electrons. This is not a scientific explanation, but it helps us to remember what's happening, right? So that's good enough. So let's think about fluorine. This doesn't have an atomic number or anything, but we've got the periodic table on the wall. Fluorine has 9 protons. That tells us a fluorine atom has 9 electrons. So fluorine, 9 protons, 9 electrons. So 9 positive charges, 9 negative charges. Overall neutral. The noble gas right next to neon, right next to fluorine, is neon, and it has 10 protons and 10 electrons, right? So neon has 10 protons and 10 electrons. Fluorine would like to look like neon. He cannot change who he is, he can't change his number of protons, but he can change what he looks like on the outside. So if he gains 1 electron, then he'll have 10 electrons, and he will look like one of the cool kids. Does it make him one of the cool kids? No. High schools are full of kids who dress like the cool kids but are not part of that group, right? So if fluorine gains an electron and has 10 electrons now, it has 9 positive charges and 10 negative charges, and so overall it's going to have a -1 charge. And that's how fluorine becomes a -1 ion, or 1- ion. So fluorine wants to gain 1 electron to be like the noble gas. Everybody else in this halogen family does the same thing. Chlorine, bromine, and iodine, they'll gain 1 electron, so they all form a 1 minus ion. So that charge is equal to their group number minus 8. 7 minus 8 is negative 1. If that explanation works for you, awesome, use it. Some students don't like that. So then here's a simpler one. Let's pretend that the periodic table is a board game. That sounds more fun, doesn't it? And the starting point is over here in the noble gases, and you have to count backwards how many spaces over. So for fluorine, you're going back 1. So this is minus 1. For oxygen, you're going back 2 spaces, minus 1, minus 2. This is negative 2 charge. And here's negative 3 charge. That just coincides or corresponds to their charges. It's not an explanation, but it's a way of figuring it out and remembering it. Nitrogen has a 3 minus charge because by gaining 3 electrons, it becomes like neon. These atoms are forming ions that have the same number of electrons as the nearest noble gas. Let's look at sodium. So sodium, an atom, we can tell from the periodic table, has 11 protons and 11 electrons. It wants to be like a noble gas. Well, neon is the closest. Neon has 10 electrons. So if sodium with 11 electrons gets rid of 1, then it's got 10 electrons like neon, and it looks like one of the cool kids. When it loses a negative charge on the electron, then overall it has a plus 1 charge. So these guys all lose 1 electron. These guys all lose 2 electrons to become like a noble gas. And then group 3A, in group 3A, aluminum is a metal, and aluminum will do the same thing. Aluminum will lose 3 electrons and form a 3 plus ion. There's a couple in here that are not listed, and I'm not really sure why. Phosphorus. What? Oh, I see what happened. Phosphorus also forms a 3 minus ion. Any questions? So we should be able to do a question like this. Predict the charges of the monoatomic ions formed by these main group elements. So nitrogen. We find nitrogen on the periodic table. Nonmetals form negative ions. Nonmetals, negative. So how many electrons is nitrogen going to gain to get to be neon? It needs to gain 3 electrons. So it's going to have a 3 minus charge. Or we can say, well, we're going to start over here and we're going to count backwards. Minus 1, minus 2, minus 3. We can say group number minus 8, 5 minus 8 is negative 3. So it's going to have a 3 minus charge. If we write the symbol for that, we're going to write the element symbol, and the charge is going to be a superscript on the right, and we put the number first, followed by the sign. We don't want it to look like an exponent. We don't want it to look like the variable n raised to the negative 3rd power. So we put the sign after. How about this? Rubidium. Yeah, it's going to be plus 1. It's over here in group 1. All the group 1 elements can form plus 1 ions. Now hydrogen is here. Hydrogen also can form a plus 1 ion. So rubidium has a 1 plus charge. If we write the symbol for that ion, it's rubidium with a plus. We'll see that chemists often just leave the number 1 out of it. And so we're writing the symbol, the sign, the plus, but we're not writing the 1. Any questions?